All right, final exam cheat sheet. Picking up here with problem number 13. This will kick off chapter 10. This was the first chapter that we started coming back from spring break. And chapter 10 was about circles, which is one of the more familiar geometric shapes to us. But we dealt with a lot of maybe unfamiliar things with circles and learning a lot of the properties about them throughout this chapter. So problem number 13, you're going to see a diagram similar to this. And I would imagine going through these last remaining problems, through these last remaining recordings, these will become more and more familiar as we work through them. Namely, this one in particular, we dealt with this kind of problem. This is pulled directly from our Chapter 10, Section 1 notes. We also dealt with a problem like this in our Chapter 10 test. Now, it wasn't this exact one, so this won't be available for like test correction or anything, but the procedure will be the same. Essentially, we're shown a circle. We would name a circle after its center, circle P here. And then we have this triangle that's kind of interacting with it. And in this problem number 13, you're going to be seeing a diagram similar to this, and you will be given all three side lengths of the triangle that you are shown. And you will be asked a simple question. Is this segment, now the letters won't matter, but in this diagram that we see here, segment ST, is it tangent to the given circle? And this key term tangent is something you can look up for formal definitions and stuff, not that you would need it, but in Chapter 10, Section 1, we introduced this term tangent, which is arguably one of the most important geometric terms when it comes to circles. Tangent. Tangent literally means that if I were to extend this segment off into forever, that this point T right here would be the only point that it would ever touch this circle. And that's what the definition of tangent means, but it also has a further deeper definition that tells us that anything that is tangent to a given circle, there is some radius that's going to connect the center of the circle to that tangent point, and it's going to do so at a right angle. So in this problem, when we are asked whether or not this segment is tangent to the circle, it's just another way of really asking, is this a 90-degree angle? And that ultimately is how we're going to use the procedure here to solve for the problem. Because let's assume first that segment ST is tangent. That's going to force this angle to be a 90-degree angle and fundamentally make this triangle a right triangle. Why does that matter? Because now I'd be able to test whether it's a right triangle using Pythagorean theorem, where I would have the legs of the triangle. The legs are the sides of the triangle that would make the 90-degree angle, where each of those sides, each of those legs squared, added together would equal the square of the hypotenuse. This would be forced to be the hypotenuse for a couple reasons. First off, it would be opposite the 90-degree angle, so this would be forced to be the hypotenuse, but also a little bit more obviously, because this is the longest of the three sides of this triangle, the hypotenuse in any right triangle is always the longest of the three sides. And that's important because if I'm using Pythagorean theorem, this would have to be the c squared in the a squared plus b squared equals c squared formula. So that's ultimately how we're going to set this up. Geometrically speaking, just to use the letters first, and you don't need to do this part, but we would say that st squared plus pt squared, these are the two legs that form the right angle supposedly, these two legs, would have to equal the hypotenuse squared. And again, when I set up the Pythagorean theorem, this is really the most important piece to set up, because it does not matter which of these two goes first in this order, okay, because that addition, the order does not matter. But obviously isolating the hypotenuse is going to be the critical piece, and that will always be opposite the 90-degree measurement in this scenario. Well, at this point now I'm just plugging in the numbers, and I'm going to end up with the following. ST here is this 35 unit side, so 35 squared plus the 12 unit PT squared. This, for the record, is the radius of the circle, just to point that out. And we're testing to see whether or not that equals this 37 squared. And that phrasing is important because, again, technically I don't know if this is true. I am testing to see whether or not ST is tangent. So really this is a question mark. Is this true? If this combination here on the left-hand side of the equation happens to equal the same result as what's on the right-hand side of the equation checks out. That would force Pythagorean theorem to be true, and Pythagorean theorem is only ever true if it's a right triangle. If it's not a right triangle, this will simply not equal the other side. So this result will just not match this guy. So that's really all I'm testing right here. At this point, it's just button mashing on the calculator, so let's do that button mashing. All right, so 35 squared, or 35 times 35, is 1225. 12 squared I have memorized. 12 times 12 is 144. And then 37 squared, the piece I'm testing right here, is this 1369. This is still technically a question mark. Quick arithmetic here. If I add 1225 to 144, this is in fact 1369. And so in this case, in this instance, I do in fact get something that checks out. 1369 does in fact equal 1369. So to answer the question, yes, this does check out. What does this result actually mean? Because it doesn't really seem like anything significant happened. We just confirmed that the left-hand side of the equation equals the right-hand side of the equation for Pythagorean theorem. But the fact that Pythagorean theorem worked forces the following to be true. The triangle has to be a right triangle, meaning that the original question, is segment ST tangent to the given circle, circle P? The answer is yes. Why is it tangent? Because Pythagorean theorem checked out, it has to be a right triangle, meaning that angle at which ST intersects with that radius has to be a right angle, and that only happens when it's tangent. Now, just to prepare you for a possible other result on your final exam, had this number been anything other than 1369, or in other words, had this left side of the equation just simply not matched the right side of the equation, all that means is that it's not a right triangle, meaning that can't be a right angle intersection, meaning it cannot be tangent. So the answer simply there would be just not tangent for that reason. But mathematically speaking, all it would mean is that it's just not a right triangle, meaning that if you were to extend that line off into forever, maybe it just intersects in multiple places on the circle or completely misses it or whatever. It does not mean that the triangle doesn't exist. It just simply means it's just not tangent. This is just a very specific result, and it would require that Pythagorean theorem check out and be true. So there's problem number 13 on our final exam. All right, moving on. Problem number 14 is also going to come from chapter 10 on circles. And so problem number 14 is going to come from chapter 10.7. 10.7 dealt with circles in the coordinate plane. And the whole purpose of a coordinate grid is because it gives us specific location and relative distance to other objects in that coordinate universe. And that's used a lot in real life. And when it comes to chapter 10.7, we were introduced to the standard form equation of a circle. And it was as follows. X minus h squared plus y minus k squared equaled r squared. Now this formula, the standard equation of a circle, basically breaks down two pieces of information. This h and k element here will end up being the center coordinate location of where this circle is located in the coordinate universe. And I'll talk about that as we come along it. And then the right-hand side of this equation, this r value, is radius of that circle. In other words, it gives me the size of the circle. Really the only measurable aspect of a circle I'm going to care about. Okay, so I get location and size of a circle, basically everything I need to graph a circle. So there's the standard form equation of a circle. And fundamentally, on problem number 14 on your final exam, you're going to be asked to write the equation of a circle given the following information. And here's the information you'll be provided. You will be told the center location of the circle that you're going to be writing the equation for. And for the sake of this example, we'll go ahead and pick a coordinate point. We'll give it the coordinate point 5, -4. And I'll explain how this translates directly into this equation. And then you're going to be given some other point on the circle itself. And again, for the sake of this example, we'll just pick a point. We'll give it 9, -7. So just briefly to discuss what the meaning of these things are. These are just locations on the coordinate grid. It is important, worth noting, that the center of a circle is not actually on the circle itself. It's simply the center of that shape, right? Whereas a point on the circle is actually part of that circle shape. So if I were to draw a circle, the center would be obviously at the center of that shape. A point on the circle would just simply be part of that graphed, drawn element. So again, let me relate this information back to this standard form that we're supposed to convert this into. First off, the fact that we're given the center, this coordinate point, this xy coordinate point, is directly going to translate into this left-hand side of the equation. H and K give me that location. And just to briefly talk about, I'll do this at the very end, This 5 is going to be the h value. This -4 is going to be the k value. The fact that we see these minus signs here just means I'm going to flip the sign of both of these values. So the fact that I have +5, -4 as my center again, that's going to turn into x -5 and y +4 in those parentheses. That will be the last thing that we do. I'll circle back to that, pun intended, at the very end of this problem. But let's get to what we also need here for the circle. We're explicitly given center, this coordinate point, which is going to fill out this left-hand side of the equation. But the right-hand side, this radius, is just not explicitly given. The radius of a circle is the distance from the center to some point on the circle. And that's an important phrasing because we literally have the center and some other point on the circle. If we find the distance between these 2 points, these 2 coordinate points in the coordinate universe, that gives us radius r of this circle. So based on the information I'm given, I actually need to use the distance formula. And this will really be the legwork in this problem, so we'll do the following. Now, distance formula in the past has been expressed with d equals, but since the distance between these 2 points is the radius of the circle r, d here is going to be the radius r of this circle, and it'll be as follows. So here's the traditional distance formula at this point. This long square root, and then I'm taking the difference of the respective x values between the 2 coordinate points, squaring it, and then adding it to the distance between the respective y values squared. It's this complicated formula. There's a description in previous chapters on where this formula comes from. It's essentially a form of the Pythagorean theorem. But for our intents and purposes here, we're simply just going to be converting both these coordinate points and plugging them into the appropriate spots here in this equation. So really briefly, a very common mistake that's done right here is anytime I have these 2 coordinate points, it's tempting for students to just take each of these parentheses and plug them into each of the parentheses. That's not the case. X's are going to be pulled from the x values here. Y's are going to be pulled from the y values here. So I really need to be careful about sign, and I always take a step in my own scratch work to just take a time substituting in these numbers, these values. So when I do that, again, be careful that my x values, I'll start with my center point. This will be my x1 and y1 right here. This will be my x2 and y2 value here. But it really doesn't matter what direction I go. So when I find the difference between my x's, I have +5 and +9. I'll make this guy my x1 value. So I'll have +5 minus +9 squared. For my y values, it can help to say these out loud, by the way. My y1 minus y2, I started with 5 here. That came from this coordinate point. So I'm going to start with this being my y1. -4 minus, and I always take the time to draw that minus sign so that when I come across something like this and I subtract the negative, I know to change that sign. So I have -4 minus a -7, and I'm going to square that. Again, I always take the time to do this. Technically, you could just immediately convert that to addition. That's what will happen. I just take the time to convert that just so I can see it done. All right, at this point now it just becomes the calculation part. Do your order of operations. PEMDAS dictates that I do the parentheses first, so let's do that. 5 minus 9 is -4. Don't worry about that negative. When I ultimately square it, that negative is going to go away. And then -4 minus a -7, this is now turns into plus. So -4 plus 7 gives me +3 squared. Continuing on, now I deal with the exponents. So now -4 times -4, -4 squared gives me +16. 3 squared gives me 9. Still taking the square root of that. And then combining the 16 and 9, I get square root of 25. And taking the square root of 25, this r value, which I've left out the r right here the whole time, but r is going to end up equaling 5. Now, that's not my final answer. This will come in handy for rewriting it into my final equation. So just lastly, to fill this in, I'm going to end up, based on that center point of +5, -4, I'm going to end up with x minus 5, and then y plus 4. There's the opposite sign of each of those center coordinate values. And then the r squared is this r squared, which will end up being what was underneath the root right there. So 5 squared, 5 times 5 is 25. There's the standard form equation of the circle given the following information. again, it really hinged off using the distance formula to figure out this guy.